Thanks for joining me in today's lesson. In this tutorial, we will use mathematical induction to prove various formulas. Mathematical induction is one of my favorite topics, and we are in section 11.4. I'd like to look at a certain pattern to begin today's lesson, a bunch of sums in particular. The first sum is just 1. Okay, that's easy. The sum sub 2 is 1 plus 3. The third sum is 1 plus 3 plus 5. The fourth sum, 1 plus 3 plus 5 plus 7. Clearly we are adding consecutive odd numbers. The fifth sum adds the first 5 odd numbers. So this is the pattern that I'm looking at. What happens when we add consecutive odd numbers? And so on and so forth all the way until we get to our sum sub n. So we've got 1 plus 3 plus 5 plus 7 plus 9 plus a bunch of other terms plus what would be our a sub n term? Meaning, let's write our rule to describe this pattern. Well, first of all, it is an arithmetic pattern because we're adding the same number to get from term to term, and that is a 2. So I know in my rule I'm going to have 2n. So I need to plug in a 1 to get my first term. If I plug a 1 into 2n, clearly 2 times 1 is not equal to 1. So here's my adjustment. I'm going to subtract 1 from it, and that should work. That is what our a sub nth term would be. Check it for the second term. The second term should be 3. So plugging in a 2 for the second term, 2 times 2 minus 1 is my 3. Check it for the fifth term. If I plug in a 5, I should be getting 9. 2 times 5 minus 1 is equal to 9. So this is the sum of the first n terms, and they're all odd numbers. So now let's look at what these sums actually equal, and I'll put them all over here. Obviously, the first sum is just a single number, so that's 1. Okay, great. 1 plus 3, we get 4. 1 plus 3 plus 5, we get 9. The next number, adding 7 to that, we get 16. 1 plus 3 plus 5 plus 7 plus 9 adds up to 25. What do you start to notice about these sums? Well, hopefully you're noticing that these are all the perfect squares. This is 1 squared, this is 2 squared, and so on and so forth. These are all the perfect squares. So it looks like, this is pretty cool, if we add up the first 3 odd numbers, we get 3 squared. If we add up the first 5 odd numbers, we get 5 squared. There's no reason for you to go and add the first 17 odd numbers together because, according to this pattern, it appears that that would be equal to 17 squared. So if I'm adding the first n odd numbers together, that sum should be equal to n squared. And this is a sum formula that we're going to use mathematical induction to prove. Now we can't just say, well, it looks like it works for everything that I've seen, because that's not much of a proof. We actually have to mathematically prove these statements today. So mathematical induction is a 2-part process that will prove various formulas involving natural numbers. There are 2 parts to it, and we'll come back to this one in particular. We'll prove that first. There are 2 parts to it. So we're going to be given a statement. Any statement, I'm just going to call the statement a P statement, P sub n. Today we're going to mostly be looking at sum statements, S sub n's, but it really could be any statement that uses positive integers, 1, 2, 3, 4, 5, 6, 7, 8, 9. Those are the natural numbers. The first part, we must show that P sub 1 is true. This is a pretty simple part. All we have to do is plug in a 1 and see that we get the first term. So that's pretty easy to do, step 1. Step 2, we have to show that the statement, if it's true for some arbitrary number, we'll pick k, if it's true for p sub k, then that must imply that it's also true for the very next one, p sub k plus 1. We have to show that that is true. And that's really where the meat of these problems is going to lie. How the book you read in the book, this section, how the book sort of illustrates this is with dominoes. If you had a bunch of dominoes, in fact, if you had infinite dominoes all lined up, I'm going to attempt to draw some dominoes here, and you knock one of them over, then of course they all start to fall. I can't really draw dominoes apparently. There we go. Okay. So it's like infinite dominoes, if you want to think about it like that. Imagine putting infinite dominoes, or even just 50 billion dominoes. How about that? How do you spell dominoes? Is it with an E? Okay. So if you put up some dominoes, imagine each one of these dominoes is a separate term in a formula that you're trying to prove. Well, if you know that the first domino actually exists, that's what step one is. This is basically proving that the first domino exists. And then if you say this, if you prove the second statement, that's proving that any domino, the kth domino, will knock over or will prove or will imply the very next domino, the k plus 1th domino. If you can prove that any domino knocks over the next domino, and you can prove that the first domino is there, then you've basically proven every domino can be knocked over, because the first one will knock over the second one, and the second one knocked over the third one, and the third one will knock over the fourth one, and so on and so forth. They'll all fall down. So if we can prove both of these things, then we have proven that the formula is true. So I know that this E looks kind of weird in the word dominoes, but if you want to take that out, then I guess you'd be stacking infinite pizza boxes. And that would be fine too. You can go ahead and do that. So let's look at our first example. We're going to go back to that same sum formula that we started with. 1 plus 3 plus 5 plus 7 plus dot 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 plus that expression 2n minus 1 that represents any odd number. We want to prove that that's equal to n squared. So this is our first mathematical induction. So the first step, we have to show that s sub 1 is true. That's what we're going to do here. We know that s sub 1 is equal to 1 because that's what our first term is. So we know that it's equal to 1. And we want to see if that's equal to, we have to plug a 1 into this side of the formula. So 2 times 1 minus 1. And we have to see if that's equal to when we plug a 1 into the right side of the formula, which would be 1 squared. So we have to see if both of these two things equal to 1. Well, 2 times 1 minus 1 is equal to 1, and obviously 1 squared is equal to 1. So we get 1 equals 1 equals 1, which is true. So that's our first domino. That's placing our first domino, making sure that that is true. Next, we have to show that s sub k implies s sub k plus 1 is true. This is where the algebra is really going to be coming in. So what we have to do is show that if we have the sum formula for any arbitrary number, we'll just pick k, we have to imply that the k plus 1 that comes right after that is also true. Now this may seem weird that we're just changing the letters, but that's true. We have to change the letters. This formula is given to us using n's. You cannot use that letter in the proof of this formula. So that's why we have to change that letter. So let's write our s sub k statement. We're going to need that. That's basically exactly this s sub n statement, but with k's instead of n's. So 1 plus 3 plus 5 plus 7, exactly how it's written, plus dot 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 plus 2k minus 1 will equal to k squared. Again, that might seem weird, but you cannot use an n in the proof of the formula that uses an n. It's like using a word in its own definition. You can't do that. So here's our s sub k statement. What we next need to do is figure out what the s sub k plus 1 statement is. What I like to substitute in first is, let me just write it and then I'll explain it. S sub k plus 1 is the same thing as saying s sub k plus a sub k plus 1. What that means is this sum is just one more term than the s sub k sum. S sub k is all of these terms. S sub k plus 1 is all of these terms plus one more. So all of these terms represent s sub k. Here's that. Here's my next term, the k plus 1 term. For example, if I come over here off to the side, if I have s sub k, and let's say that that is a sub 1 plus a sub 2 plus a sub 3 plus dot 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 dot. Let's just end with a sub k. S sub k plus 1 is exactly the same stuff, the same exact terms, plus one more. So S sub k represents the sum of the first k terms. S sub k plus 1 represents the same k terms added up plus one more. So that's how I always like to think of S sub k plus 1. It's all of S sub k again, plus one more term. Okay, so let's keep going with this. Now, S sub k plus 1, if S sub k is equal to k squared, S sub k plus 1 would be equal to k plus 1 squared. You're just plugging in a k plus 1 wherever you see a k. Okay, next we substitute. S sub k is going to have a new name. And I know that S sub k is equal to all infinite of these terms, but I also know that it's equal to this. So I'm going to take this and say that S sub k is equal to that. So k squared is going to take its place. Next, I need to figure out what this term is. Well, if the kth term would, in this case, be 2k minus 1, the k plus 1 term would be, well, let's just plug in a k plus 1 right there. This k plus 1 is plugging in right there for that k. Think about it. This is the expression to find any term. If I want the third term, I plug in a 3. If I want the 10th term, I plug in a 10. If I want the kth term, I plug in a k, and there it is. If I want the k plus 1 term, then I plug in a k plus 1. So I'm going to put, here's my plus sign, and then 2 times k plus 1 minus 1. And that will be equal to my k plus 1 squared that we had above it. I'm going to continue through this problem, and then I'm going to go through it once I've finished. So what we need to do now is pretty simple. We just need to prove that these things will combine to be k plus 1 quantity squared. So let's distribute, and let's get our like terms and so on and so forth. Here we go, k squared plus I've got 2k plus 2 if I distribute, and then minus 1. And these are like terms, of course, so I get k squared plus 2k. 2 minus 1 makes 1. And guess what? This will factor into k plus 1 times k plus 1, which is equal to k plus 1 quantity squared. And I proved it. That's it. Now, obviously, this is what I was talking about when the algebra comes in. This is where the algebra will be, figuring those things out. Let's go through this problem one more time. So we're given a formula to prove. I need to prove two things. First step is pretty easy. Show that S sub 1 is true. Plug in a 1 into here, and make sure that that's equal to what the first term is supposed to be. So plugging in a 1, I get 1 equals 1 equals 1, so I'm good. First check mark. Step 2, show that S sub k implies that S sub k plus 1 is true. So the first thing, you need to write your S sub k statement, which again is as simple as taking your formula, replacing the n's with k's. That's important. Next, I write the S sub k plus 1. And for the reasons over here, I like to think of S sub k plus 1 as S sub k plus A sub k plus 1, one extra term. And that is, of course, equal to k plus 1 squared because I plug the k plus 1 into this and get k plus 1 quantity squared. Now I do my substitution. S sub k turns into k squared because that's what S sub k is equal to. A sub k plus 1 becomes this term. You can see the 2k minus 1, and here's the 2k plus 1 minus 1. I plug the k plus 1 right into there. And now all of this stuff, it's like our trigonometric identities. We just need to make the left side of this equation turn into the right side, and once we've done that, we've proven that that's true. To be honest, when I first learned our mathematical induction, it was a little bit, I didn't quite understand it at first. It took some practice. It took seeing it a few times before it clicked, and I started to realize, oh, they're all the same types of processes. It's just different algebra right here. So let's do another one. Here's example 2. I want to prove that 3 plus 6 plus 9 plus 12 plus plus 3n is equal to 3 halves n times n plus 1. So what am I adding? It looks like I'm adding the multiples of 3. The multiples of 3, that would be what 3n is equal to. Okay. So let's start with the first one. Show that s sub 1 is true. So s sub 1 this time is supposed to be equal to 3. And I'm going to see, I put question marks when I'm not sure. I have to plug a 1 into this part, so that's 3 times 1. And I have to plug a 1 into this part. So that's 3 halves times 1 plus 1. Now I know what most people are going to do is they're going to assume that these things are true, and they're just going to say that 3 equals 3 equals 3, and they're going to put a check mark. Okay, that's great. I would make sure that you mathematically can prove that that's true. I know that 3 times 1 is 3. This is 1 plus 1 is 2. 2 times 1 is 2. 3 over 2 times 2 does indeed make 3. I'm not going to give you a formula that doesn't work, so I know that most people are just going to do that and put a check mark, but I just want to make sure that you know that it is true. Step 2, show s sub k implies s sub k plus 1 is true. Okay, so here we go. We have to write our s sub k statement. So I'm going to take this entire statement that was given and replace the n's with k's. So 3 plus 6 plus 9 plus 12 plus dot 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 plus my 3k is supposed to be equal to 3 halves times k plus 1. So if that's the s sub k statement, then here's the s sub k plus 1 statement. The first thing I like to think of it is as s sub k plus a sub k plus 1. And then I'll say what it's equal to. So s sub k plus 1, this is the s sub k, so I need to put a k plus 1 in place of this k, and a k plus 1 in place of this k. So the 3 halves, the k is replaced with a k plus 1. Of course, I'm putting parentheses around it. Whenever I replace a monomial with a binomial, the binomial better be housed in parentheses. And then this is also a k plus 1. So there's a k plus 1, and then a plus 1. And I'll clean that up in my next step. So now I do my substitution. S sub k is sitting right here, and that's going to come and take the place right here. So this is 3 halves k times k plus 1 plus a sub k plus 1. I need to figure out what that is, and that comes by taking the k plus 1 and just plugging it right into this. This is the expression for any specific term. This term is going to be 3 times k plus 1. I'll go back to, I guess, doing this. Here's my 3 halves, here's my k plus 1, and then this, of course, is just k plus 2. Some people go straight from plugging the k plus 1s right into this. That's fine. I'll just use this as a middle step. So now I just have to prove that this brown and this fuchsia combine to get this black. I'm going to work on the left side. Now, there are a few ways to prove that this left side turns into this right side. Some people are going to want to distribute and get their like terms together and then refactor. That's absolutely fine. But I see that there's a k plus 1 and another k plus 1. A k plus 1 in this brown term and a k plus 1 in this fuchsia term. K plus 1 is a GCF. And if you see that, it might make things a little bit easier. What I mean is I can pull this GCF, this k plus 1, out from both of these terms. I'm going to pull it out. I'm going to factor it out like a GCF. I know we don't usually factor out binomials, but we can, as long as they're the same. The 3 halves k would be left from the first term plus the 3 from the second term. Okay, so we're getting close. I see the k plus 1 and the k plus 1. There must be a 3 halves that's going to be pulled out, and I can see it, and that's what I need to do next. So the 3 halves is now going to be pulled out of this second factor, and I'll put it out front. If you don't mind, I'm going to leave the k plus 1 there because that's what it's going to be in the correct order. And then this must be k plus 2. And that is true. I know that that's true, and I'm going to do this, but let's prove why this is true. Let's come over here, and we had the 3 halves k plus 3. And when we're factoring out a 3 halves, we did it from both terms. I should put a second arrow. If we're factoring out of 3/2, ultimately we're dividing both terms by 3/2, so it can come outside. Obviously the 3/2 and the 3/2 will cancel away. That's why it's a 1k right here. If we take 3 and divide by 3/2, that's the same thing as multiplying by the reciprocal 2/3. And then you see the 3's cancel away, and of course that's equal to 2. So that's why mathematically this does hold true. And we've just proven our second mathematical induction. Please go back and watch this entire example if you need to see it again. Okay, so we've seen 2. Now let's go to our third example. This is our final example. So we have a new sum formula. 1 squared plus 2 squared plus 3 squared plus 4 squared all the way down to n squared. And that is equal to this nice looking fraction. So it looks like we're adding perfect squares together. And let's see what happens here. So first domino. Show s sub 1 is true. So s sub 1 is supposed to be equal to 1 squared. And we want to know if that's equal to, well, 1 squared. Obviously, that's going to be true. But we also want to know if we plug in a 1 here, do we get the same thing? So we've got 1 times 1 plus 1 times 2 times 1 plus 1 all over 6. And 1 equals 1 equals 1 is what everybody's going to put. There you go. But if you want to just check it, this is 1 times 2 times, let's see, 2 times 1 plus 1 is 3. So 2 times 3 is 6. And of course, 6 divided by 6 is 1. So that does work. Step 2, show s sub k implies s sub k plus 1 is true. So here we go. Here's our s sub k statement. That's 1 squared plus 2 squared plus 3 squared plus 4 squared plus dot 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 plus k squared is supposed to be equal to k times k plus 1 times 2k plus 1 divided by 6. So there's our s sub k statement. That's as simple as recopying the s sub n statement with k's instead of n's. S sub k plus 1 is s sub k plus a sub k plus 1, right? The entire list of all the terms added up, and then one more specific term. And that's going to be equal to, I'm going to plug a k plus 1 everywhere I see a k. So this k turns into a k plus 1, put it in parentheses. This k turns into a k plus 1, and if you don't mind, I'm going to write it as k, well, I'll write it as k plus 1, then plus 1 again. And then this is a 2k plus 1 plus 1. Okay, all divided by 6. I'll go back and clean up these terms in my next statement when I do my substitution. So s sub k, this is a nice blue expression of what s sub k is equal to. So I'll put that here. K plus 1, 2k plus 1 over 6. A sub k plus 1 is not too difficult. I'm going to plug a k plus 1 right in here and just basically put k plus 1 quantity squared. And let's do one more to clean this up. This is k plus 1, of course. This is k plus 2. This is, if I distribute 2k plus 2 plus 1 more. So isn't that just 2k plus 3? All over 6. So this is now what we need to prove. We need to prove that this left side combines to give this right side. So the first thing I see is I've got two different fractions with different denominators, so let's get them to have the same denominators. I'm going to multiply the denominator by 6 by also multiplying the numerator by 6. So let's see what we've got. We've got the k plus 1. This is some good algebra in this one. Over 6, and this is now 6 k plus 1 quantity squareds over 6. Okay, so at least now they have the same denominators. And since they have the same denominators, I can combine these two things together all with one denominator. So I've got the k plus 1, the 2k plus 1, plus the 6 and the k plus 1 quantity squared. So that's all 1. Okay, I'm going to need a little bit more space, so I'm going to take this and bring that over here to the next page. If I can do that. Okay, great. I got most of it. I forgot the 6. So we'll put that up here, and that's over 6. Okay, sounds good. And let's see what it's equal to. It's supposed to be equal to. So that is right here. And let's see if I can, it's going to grab too much of it. K plus 1, K plus 2, 2K plus 3. Okay, we've got it. So this is supposed to be equal to K plus 1, K plus 2, and 2K plus 3 over 6. That's what we're shooting for. Okay, so the next thing I see is that we have that common factor again. I see there's two different terms. There's this term and there's this term in this numerator. So I've got the K plus 1 and another K plus 1. So I'm going to factor out the K plus 1s like I did in the previous example, and I'll have the K, let's see what's left, a K, a 2K plus 1, and then a plus sign, and then a 6, and the other. I only took one factor of K plus 1 out, so since there were two, there still is another factor of K plus 1, all divided by 6. So that's where we are. And that's good. I've got the K plus 1 factor here. The other two factors are listed right here. That must mean that the rest of the stuff in this parenthesis, I think I forgot a parenthesis, must factor into that. I'm not going to see that until I actually do some distribution and get this to be the trinomial that it will become. And let's see what we've got. We've got the K plus 1 and the 6. That's great. This is 2K squared plus K plus 6K plus 6. And then I've got my like terms together to make 7K. Okay. 2K squared plus 7K plus 6 all over 6. And guess what this trinomial is going to factor into? I bet it's going to factor into this. Please make sure that the factors are put in the correct order, because remember, this is a proof and both sides have to be identical. K plus 2 and 2K plus 3 over 6. And you can do a quick check if you want to FOIL backwards. K times 2K is 2K squared. Here's my 3K, and here's a 4K. That adds up to the 7K. And then the last terms give me 6. So this is correct. And like I said, a lot of good algebra in that one. So there's our 3 examples for mathematical induction. I know that this is going to take some practice, so that's why we're going to be doing that in class. I do have 2 try problems that I've put on your note sheet. If you'd like to try these problems on your own, pause the video now and come back to check your answers. That would be a great idea to prepare for class. So if you would please pause the video, I'm going to do these try problems while you do them as well. Thanks for pausing. So here is try 1 worked out. Give you a little bit of time on that. You can pause to check your stuff. And I will flip over now to try 2, which looked like it was going to be tougher than it was, but not too bad. I sort of ran out of room and worked left to right on this one. So thanks for trying those. I'll see you in class and we'll practice more. See ya.